Use the graph to evaluate the following limits. In part A, we're evaluating the limit as x approaches -2. Now, if we're approaching -2, we want to be close to x equals -2. And since this is a piecewise function, that means that we're not going to consider this part of the graph way over here, or even this part of the graph here. We want to be close to x equals -2. Let's start with x values that are a little bit smaller than -2. And again, I'm going to pretend like I'm a little bug and I'm traveling on this path of my function here, and I'm getting closer to x equals -2, and I'm looking at what my y values are doing. So here it looks like my y values are getting closer to 1. Now I want to do the exact same thing on the other side where the x values are bigger than -2, and I want to crawl and get closer to -2, and the y values here are also approaching 1. Therefore, the value of this first limit is going to be 1. My y values are getting closer to 1 as my x values get closer to -2. Part B, we want the limit as x approaches 3. So we're going to be looking at this portion of the graph here where the x values are near 3. Let's start with x values a little bit smaller than 3. So if I am crawling along this graph, approaching x equals 3, it looks like my y values are getting closer to 1. On the other side, where the x values are bigger than 3, my y values are also approaching 1. Therefore, the value of this limit is also 1. Part C, we want to find the limit as x approaches -1. If I start with x values a little bit smaller than -1, and I am crawling along this graph, it looks like these y values are approaching 0. On the other side of -1, when I crawl along the graph, my y values are approaching 1. That sounds funny to say they're approaching 1 because they actually equal 1, but we do say the y values are approaching 1. So on the left side, the y values approach 0, but on the right side, the y values approach 1. And that tells us that this limit does not exist because the y values are approaching two different numbers on either side of -1. And what we call that is the left-hand limit doesn't equal the right-hand limit. And I want you to write this out in words first, and then we'll come back and we will write this out with the correct notation once we learn it. So we say that this limit does not exist because the left-hand limit does not equal the right-hand limit. I'm approaching different values on either side of -1. Last one, let's do the limit as x approaches 1. So again, let's start with x values a little bit smaller than 1. So that would put me here crawling along this graph. My y values approach 1. And on the other side of 1, as I crawl along the graph, my y values approach 2. Now notice we are totally going to disregard this point here because this point here, this would be used if we were evaluating f of 1. So f of 1 is equal to -2. But remember, when we're finding the limit as x approaches 1, we do not consider what's happening at x equals 1. We don't care. We want to know what's happening on either side of 1. So this is another example of a limit that does not exist. And again, as we write out why it doesn't exist in words, it doesn't exist because the left-hand limit does not equal the right-hand limit. When we say we're computing a left-hand limit, this is the notation that we are going to use. So see how you have a little negative sign as a superscript up where an exponent might be? When we have that notation, that means we are approaching a from the left. And that means we only consider values of x that are smaller than a. So when you see this notation, x approaches a from the left, that means we are computing a left-hand limit. only considering values of x that are smaller than a. However, when you see the notation with the plus sign in the superscript, that means we're computing a right-hand limit, so we only consider values of x that are larger than a. And this is called a right-hand limit. So let's use the graph at the right and compute each of these one-sided limits. So the first is saying let's compute the limit as x approaches a from the left of f of x. So on this graph, I'm considering a to be this x value here. And that means I'm going to ignore all of the values that are larger than a and only consider the values of x smaller than a. So that means I would be here on the left-hand side, and I'm crawling along the graph getting closer to x equals a, and it looks like my y values are getting closer to this y value, which is marked as L sub 2. So the left-hand limit would be L sub 2. However, the right-hand limit, the limit as x approaches a from the right, that means I'm going to totally ignore the values that are smaller than a, and that puts me on this side of the graph. And I'm crawling along, and as x gets closer to a, my y values are getting closer to this y value, which is marked as L sub 1. So that's how we do one-sided limits. However, if I were to ask you, does the limit exist as x approaches a? So if there is no subscript written, then that means I need to approach from both sides, and this would be an example of a limit that does not exist. And it doesn't exist because the left-hand limit does not equal the right-hand limit. So our definition is that the limit as x approaches a of some function f of x, this means I'm approaching from both sides, this limit will equal L if and only if the right-hand limit is equal to the left-hand limit. But let's write that out in symbols rather than words. So this will be true if and only if the limit as x approaches a from the left of the function is equal to L, and the limit as x approaches a from the right of the function is equal to L as well. So this is how we write the left-hand limit is equal to the right-hand limit. So next we're going to go back to that last example and write this out with correct notation as we're justifying why those last two limits did not exist. Back here on example 1 in part C, we said the limit did not exist because the left hand did not equal the right hand limit, but let's now write that with the correct notation. So the left hand limit would be the limit as x approaches -1 from the left of our function f of x, and that limit did not equal the limit as x approached -1 from the right. So you do have to be really careful reading this because you can see there's a lot of negative signs in particular when we're looking at that left-hand limit. So you have to read this statement very carefully, that x is approaching -1 from the left. And on part D, let's go ahead and write that notation correctly. The left-hand limit would be the limit as x approaches 1 from the left of our function f of x does not equal the limit as x approaches 1 from the right of our function. So now we know how to do one-sided limits.